Welcome to the Deep Dive, the show where we cut through the dense stuff and give you the essentials fast.
Glad to be here.
Today we're wrestling with a beast, a really foundational text, Theory of Games and Economic Behavior by John von Neumann and Oscar Morgenstern from 1944.
Yeah, this is the one. It's the bedrock. Game theory starts here.
And our mission, really, is to unpack the core ideas, the big shifts they introduced to economics using, well, the logic of strategy. Think of it as your shortcut through some seriously heavy math.
It's hard to overstate how ambitious this book was. They were genuinely trying to do for the social sciences what math did for physics, like find the universal laws.
Wow. Not just a new model, but a whole new science of interaction.
Exactly. A rigorous axiomatic science for how people behave strategically. It is dense, no doubt. But the core concepts, the philosophical shifts, brilliant. And that's what we'll focus on.
Okay, let's dive in then. Why? I mean, what was so wrong with economics back then that they felt they needed to invent, well, game theory?
Well, their basic critique was pretty sharp. They basically said economics lacked a universal system. It was too descriptive.
Descriptive, meaning?
Meaning it was good at, say, describing what happened in a trade, but not great at predicting or explaining the why in a rigorous mathematical way, especially when things got complicated.
Complicated.
Like when multiple people are involved, the social element. They pointed to this issue they called the indeterminateness of bilateral monopoly.
Okay, hold on. Indeterminateness of bilateral monopoly. Can we translate that?
Yeah, it's a mouthful.
Yeah.
Basically, think of the simplest possible market. One seller, one buyer. That's it. Both have power. They haggle over a price.
Right.
Traditional economics couldn't really pin down where that price would end up. It just said, well, somewhere between the seller's minimum and the buyer's maximum.
So it couldn't predict the outcome of a simple haggle.
Exactly. The math kind of broke down right where the strategy and the social interaction began.
Yeah.
So von Neumann and Morgenstern saw this and said, look, these problems have to be treated mathematically, but first, we need better tools. We need the right math.
Which leads us to maybe the biggest hurdle they tackled, measuring utility, satisfaction, preference, how much someone wants something. Economists always seem to struggle with putting a hard number on that.
Oh, absolutely. Because the old ways, like using indifference curves, were just ordinal. They let you rank things like, I prefer apples to bananas. But they couldn't say how much more.
So you couldn't say, apples give me 10 happiness points and bananas only 5.
Right. And they argued pretty fiercely, actually, that for economics to be a real science, you needed that cardinal utility. You needed those numbers. It was essential.
Okay, so how did they crack it? How do you invent a ruler for happiness that works mathematically?
This was their really revolutionary move. They connected utility directly to probability, to risk.
Probability. How does that work? If I like something, isn't that separate from whether I'm willing to gamble for it?
Well, that's the clever part. They redefined utility. It's not about measuring your internal feeling of happiness. It's about measuring the consistency of your choices when faced with uncertainty.
Consistency. Explain that.
Okay, so they set up these axioms, these basic rules of rational choice. Like, if you prefer A to B and B to C, then you have to prefer A to C. Transitivity. Makes sense.
Oh, yeah, seems logical.
So if your preferences are consistent like that, they found they could use your choices between, say, getting outcome A for sure, versus taking a 50-50 gamble on getting outcome B or outcome C to actually calculate numerical utility values for A, B, and C.
So your willingness to take the risk reveals the underlying numerical value you place on the outcomes.
Precisely. Your preference for risk, or your aversion to it, becomes the measuring stick itself. It's less about how you feel and more about whether your choices make mathematical sense together.
That's a completely different way of looking at it. Utility isn't feeling, it's consistent choice under risk.
You got it. And once they had that piece, a way to mathematically model rational individual choice, they could then tackle the bigger problem, social interaction.
Right, moving beyond the Robinson Crusoe economy they talk about.
Exactly. The lone person on an island. Crusoe's problem is just technical, how best to use resources against nature. It's optimization, but simple optimization.
But when someone else shows up?
Everything changes. The moment Crusoe meets Friday, the problem becomes social, strategic. My best outcome now depends entirely on what Friday does and what I think Friday is going to do and what Friday thinks I think.
Yeah,
You see,
it spirals quickly.
totally. You're not playing against nature anymore. You're playing against another thinking mind. And that, they argued, is why economics needed to shift its focus from those old equilibrium models to the framework of games of strategy.
Makes perfect sense. Like in chess, my best move is all about your likely response.
Right. And that led them to formally define what a game is in their system. It's, a sequence of moves, choices, maybe some chance events thrown in, rules, and importantly, payoffs at the end.
And the key idea for the player is strategy?
Yes, but their definition of strategy is incredibly rigorous. It's not just your next move. A strategy is a complete plan, like a full instruction manual that tells you what to do in literally every possible situation that could ever come up in the game.
Wow. That's comprehensive. A perfect playbook.
It has to be. For the math to work, if you have that complete strategy, you're set to play optimally, no matter what.
Okay, so now we get to the actual math part they build. Chapter 3, they immediately narrow it down. Right down to the simplest case, zero-sum, two-person games. Why start there? Just two people locked in pure conflict where one person's gain is exactly the other's loss? Seems a bit bleak.
Well, they needed a starting point where the interaction was mathematically pure, you could say. Simple and clear. Zero-sum means the total pot never changes. It's pure conflict, what I win, you lose, and vice versa. There's no room for cooperation, no way to make the pie bigger.
Okay, pure conflict. And how do you play rationally in that scenario?
That brings us to their famous max-min principle. It's the foundation of rational play in these zero-sum games.
Max-min, maximum of the minimums. How does that work?
Think of it defensively, super defensively. Player one looks at all their possible strategies. For each strategy, they figure out the absolute worst possible outcome, assuming the opponent plays perfectly to counter them.
Okay, worst case for every option.
Then, player one chooses the strategy whose worst outcome is the least bad. They maximize their minimum guaranteed payoff. It's about securing the best possible floor for yourself.
So guaranteeing the best of the worst. Total damage control, assuming your opponent is out to get you.
Exactly. And the opponent, player two, does the opposite, using the min-max principle. They look at their strategies, figure out the maximum loss they could suffer for each one, and then choose the strategy that minimizes that maximum loss.
Okay, trying to limit the worst damage the other player can inflict.
Right, and the ideal situation, the stable point, is what they call the saddle point. That's when player one's max-min value perfectly equals player two's min-max value. Meaning neither player has any incentive to change their strategy if the other player sticks to theirs. It's a stable equilibrium point born purely out of rational self-interest in conflict.
But they show examples like matching pennies, where those values don't line up. The max-min isn't the same as the min-max. There's no saddle point.
That's crucial, and that's where things get even more interesting. If there's no saddle point in pure strategies, meaning always playing option A or always playing option B, then playing predictably is a mistake. Your opponent will exploit it.
So what's the rational move then?
Randomness. This is where they introduce mixed strategies. If a stable solution doesn't exist by picking one thing, it exists by picking probabilistically. You might play strategy A 60% of the time and strategy B 40% of the time, chosen randomly each turn according to those probabilities.
You flip a weighted coin, basically.
Essentially, yeah. That randomness prevents your opponent from predicting and countering you effectively. The math tells you the exact probabilities needed to achieve the best possible outcome on average in the long run, even without a saddle point.
It's pretty mind-bending that pure conflict between just two people often requires calculated randomness to find a stable solution.
And remember, this is the simplest case. They knew the real world wasn't just two people in a zero-sum fight.
Right. So what happens when they scale up? Chapters 4 and V, 3 or more players? And post-in-game.
Yeah, that's where the complexity just explodes. It's not just more players. The whole nature of the game changes fundamentally. Well, for starters, most real-world situations aren't zero-sum. Wealth can be created or destroyed. The total pie can change size. But the really big change is coalitions.
Teaming up.
Exactly. In a two-person game, it's just you versus them. But with three or more, two players might realize they can do better by cooperating against the third. The max-min logic doesn't really apply anymore because pure antagonism isn't the only option.
So the question isn't just what's my best move against everyone else, but who should I ally with and how do we split the winnings?
Precisely. The focus shifts from individual strategy against the field to coalition strategy and bargaining within the coalition. This forced them to introduce totally new concepts.
Like what?
Things like imputations, which are basically proposed ways to divide the total payoff among all players in a way that's somewhat stable. And crucially, they start talking about standards of behavior.
Standards of behavior. That sounds less mathematical, more like sociology.
It kind of bridges the gap. They realize that for in-person games, especially non-zero-sum ones, mathematical rationality alone might not be enough to determine a unique outcome. You also need to consider existing social norms or expectations about fairness or stability.
So the math describes the possible deals, but society might influence which deals are actually considered acceptable.
That's a good way to put it. The goal shifts from just maximizing your own gain to finding a solution, an imputation that no subgroup or coalition has an incentive to break away from to form their own better deal. It's about finding group stability.
That is a huge undertaking for one book. Okay, let's try and wrap this deep dive up for you, the listener. What are the absolute key takeaways?
I'd say first, economics desperately needed mathematics to become predictive, not just descriptive. That was their core argument.
Second, they found a way. They made utility cardinal, gave it numbers, not by measuring feelings, but by analyzing consistent choices under risk and probability.
Yeah.
Huge shift.
Third, complex social interactions, all that strategic back and forth, are best modeled as games of strategy, starting with the purely defensive max-min thinking in zero-sum games.
And then moving to the much more complex world of coalitions and bargaining when you have more players and the possibility of mutual gain.
Right. The framework scales up even if the math gets incredibly hard.
Okay, so final thought, something provocative for you to consider based on all this.
Well, here's something interesting. When von Neumann and Morgenstern get to those complex in-person games, they explicitly say that achieving stability often relies on these standards of behavior that come from, the physical world, social structures, existing organizations. It implies that the pure math of rationality might define the possible stable outcomes, but you might need those pre-existing, maybe non-mathematical social rules, rules about fairness, trust, how things are done, for society to actually settle on one of those outcomes.
So the question becomes,
Yeah, is game theory just a map of pure, cold rationality? Or is it also, maybe more profoundly, a map of the social rules and structures that we need for rational behavior to even lead to stable outcomes in a complex world? Something to think about.